In this lesson, we're going to combine two of the last couple of lessons. We're going to look at planes and their equations, and we're going to talk about the Cartesian idea again. Before we get started on that, though, one of the big challenges here is to know what system you're working in. Are you working in R2 or R3? Okay. We know in R2, whenever we graph a scalar equation, so for example, ax plus by plus c equals 0, we know that's a scalar equation. We know it's a line, it has to be a line. We could find out the x and y intercepts and things like that. In R3, when we produce a scalar equation, it looks similar. We've got an ax, we've got a by, we've got a cz, and we've got a d. So one extra variable, one extra coefficient, and this is going to produce a plane. It's always a plane. Now the challenge is you might not always have an a, b, a c, and a d value. For example, you could have something that looks exactly the same, x plus y equals 7. In R2, that was a line. In R3, it's going to be a plane, even though the equation looks exactly the same. So you have to actually stop and think, is this question talking about R2 or R3? Because it does make a difference on how you approach the question, lines versus planes. Okay, so when we first started talking about Cartesian equations, we said we can use the idea of a perpendicular line to our line. So you call that the normal. The same idea works with planes. If we know a vector on our plane, so we have a direction vector, we can create its normal and it will be perpendicular to our plane. It works the same way in that the perpendicular vector, the a, b, and c, are your components, your coefficients for the x, the y, and the z in your scalar form. And so all you need to do is solve for d, and we can use a point to do that. Okay, so basically the same ideas. So just to show you how it works, just to remind ourselves, if I've got a point 3, negative 2, 5, and that's on the plane with a normal of negative 2, 3, 5, determine the Cartesian equation. So the Cartesian idea is your x value comes from your normal, your y coefficient comes from the normal, it's y and x, and your z coefficient comes from the normal, and all we need to do is solve for d. We can do that using any point that we know. So we're given a point of 3, negative 2, and 5. So we can solve for d the same way we were solving for c when we were doing Cartesian equations in R2. So we've got negative 6 minus 6 plus 25 plus d. So d is 6 plus 6 minus 25, or d equals negative 13. And so our Cartesian equation, our scalar form of this equation would be negative 2x plus 3y plus 5z minus 13 is 0. Okay, so no differences, right? Exactly the same as what we did in R2, just doing it in R3. The only trick is we've got to find this normal vector first and know some point on our plane. To find that normal, okay? Well, on a plane, if we know two vectors, we know that we have a process of finding a normal, and we can do that using a cross product. Okay? That was kind of the idea of doing that cross product in the first place, to produce a vector that's perpendicular to two known vectors. This is sort of the application of it. So given our plane here, we have a point, and we've got 1, 2 vectors. So maybe one point's this way, one point's this way. We want to know something that's perpendicular to it, so this idea right here, that one, and that would be our normal. And the normal will be the coefficients of our scalar equation. So how do we find normals again? Well, it's a cross product. So we're going to take the cross product of S cross T, if you will. And we can use, remember our methods, we have the crisscross method, we have the cover-up method, your choice. Just do a cover-up here just to remind ourselves. Okay, so write them out left to right, and then cover up the x's and do the other parts. So 8 minus 4, 4 minus 1, but the opposite sign, and 8 minus 4 again, 8 for the z, and we'll get 4, negative 3, and 4 as our normal for this plane. So now that we have that, we know that 4x minus 3y plus 4z plus d has to be 0 for the plane. And to find d, we need some point, and we were given a point of negative 2, 3, 5. So negative 2, 5, and 3. I can solve for d. So negative 8 minus 15 plus 12 plus d equals 0. So d is 8 plus 15 minus 12. D equals 11. Okay, so the equation for this Cartesian, the scalar, would be 4x minus 3y plus 4z plus 11 equals 0. Okay, so we're doing the same things we did before with lines. We're just doing with planes. The only new trick is to find that normal. We got to be perpendicular to two vectors, and that is a cross product. Okay, let's try something else. So we got a point, and we want to know if it lies on a plane. And we can do this using two different forms, Cartesian or parametric. We'll go through both. Down the road, we won't do both. It's just the idea that there is two different ways of doing this. Our parametric form would be x. Here, x equals 2 plus s plus 3t. The y would be 1 minus s. There is no t part of that. And z would be 0 plus 2s plus t. And we know a point, so we can fill that point in, right? That's what we did in the past. 2 plus s plus 3t. 2 equals 1 minus s. Negative 1 equals 2s plus t. And we have a choice of which ones you want to solve. Pick the easiest ones. I'm going to suggest this one right here might be the easiest. S equals 1 minus 2, which is negative 1. And I can use that in either of the other ones. I think this would be the best suggestion here to solve for the t component. So we got negative 1 is negative 2 plus t, or negative 1 plus 2 is t, and t is 1. And just to check, we're supposed to check by using the third one. So 5 equals 2 plus s, so plus negative 1, oops, plus negative 1, and then plus 3 times t, t is also 1, so 5 equals 2 minus 1 plus 3. And we've proven that it does not lie on the line, because we get 5 here and 4 here. So not on the line. Okay, so using a parametric form, or sorry, not on the line, not on the plane. So we're talking about planes here. Okay, if I want to do it using the Cartesian equation, I can do basically the same thing. I just got to make the Cartesian equation first. My Cartesian equation needs my normal. My normal is made up of s cross t. So s cross t. And just to remind ourselves, we'll use the crisscross method this time. So s and t, using those values that are there, we have, you start with the y, negative 1, 2, 1, negative 1, and the y, 0, 1, 3, 0. And if we crisscross, we get negative 1 minus 0. We get 6 minus 1, and we get 0 minus negative 3, or 0 plus 3. So we get negative 1, 5, and 3. Okay, so Cartesian, negative x plus 5y plus 3z plus d equals 0. Use the point that we know we were given, 210. Okay, so we have to use that one because we know that this one is on the line. We're not sure about point A, right? So 210. So negative 2 plus 5 times 1 plus 3 times 0 plus d equals 0. Negative 2 plus 5 plus d equals 0. 2 minus 5. and d is -3. So our Cartesian equation, -x plus 5y plus 3z minus 3 equals 0. And we're checking point A, right? So if we put point A in there, point A was 5, 2, -1. So 5, 2, and -1, and we want to see if it comes out to 0. Now, based on our parametric, we know it shouldn't, but just to prove that, what do we get? We get -5 plus 10 minus 3 is -1. Well, that doesn't equal 0. So again, not on the plane. So we have two different ways of approaching things on the planes. Just like we did with the lines, we used our symmetric equation and or our parametric equation. We could prove that way, or even the Cartesian equation. We can do the same thing with planes. You just have to create them first. Okay, we should be able to convert Cartesians back and forth between all the other different versions. So we've been looking at how to create the Cartesian. What if we have the Cartesian? How do we figure out the other forms? The easiest way to do this is to pick any of the two variables and call them your parameters. Okay? Then solve for the remaining variables. So for example, we have this equation, 2x plus 4y minus z plus 4, and I want to determine the parametric and vector forms. Well, I'm going to start off by saying I'm going to pick a parameter. I'm going to say let's let y equal s and z equal t. And I could have chosen x, doesn't make a difference. I just chose not to. And so what do I get then? I get 2x plus 4s now minus t equals 0. In other words, 2x equals -4s plus t. In other words, x is -2s plus 1/2 t. Okay, so my parametric form now, well, I've just created it. I've done all the work. Here's my x, here's my y, and here's my z. And there's your parametric forms, the three components in terms of parameters. So I can quickly turn that into a vector form. So I need a point. What point do I have on all three of these? Oh, actually, you know what? I missed a number here. When I did the export, we got to fix. We had a 4 in there too. We need that 4. Okay, plus 4 equals 0. So this has a minus 4 in here. Let's fix this real quick. So we have -4 minus 4s plus t. We divide all that by 2. We get -2, -2s, and 1/2 t. Sorry, I missed that. I just missed that number there, the 4. Okay, so the point that we have. The point that we have is, in terms of the x value, we have a -2. The y and the z, neither of them have values, so -2, 0, 0 is our point. In terms of s, the x had a -2 in front of it, the y had a 1 in front of it, and the z had nothing. And the t's, I can have 1/2 for the x, the y had no t's, and the z had a 1 in front of it. And there's a vector form. Now, some people are like, oh, I don't want to have a fraction in my thing. That's fine. We can give a different version of that. The point stays the same. And remember, we can change any of these vectors as long as they're collinear. So I can say, for example, 1, 0, 2. Just double it all, right? And that would be the exact same equation for the plane as the previous one. Just a slightly different version of it. Okay, so really quickly, actually, we can turn a Cartesian into parametric or vector. You just choose which two components you want to create as your parameters. Okay, parallel and perpendicular planes, a way of looking at how these things meet a little bit. So the first one, the easy one, is if planes are parallel. Okay, to tell if things are parallel, we can look at their direction vectors. Okay? In particular, we know that the normals should be the same if the two planes are perpendicular, because they have to be in the same direction. And so if you find the same coefficients, it means you have parallel planes for the normals. Okay? If they're not the same, if they're different, or if they're not scalar multiples of each other, then they might possibly be perpendicular. And the easy way of showing that is take the dot product of your two normals and see if it comes out to 0. If that's true, well, then maybe you have a perpendicular plane that goes this way, and another one that goes this way, right? Those would be perpendicular to one another, okay, as opposed to parallel and parallel, which have the same normals. So if you take a look at this example, I want to know if they're parallel or perpendicular. First thing they look for is parallel. Is there a multiple between my two equations in terms of their coefficients? So I can say, well, 2 times 2.5 makes 5, but 5 times 2.5 does not make 6. So those are definitely not parallel. Okay, there was no common multiple there. So the next thing I do is I check out my normal 1, which is 5, negative 6, and 2, and my normal 2, which is 2, negative 5, and negative 20. And I ask myself, are these perpendicular? If they are, I'll come out to 0. So let's check it. 5 times 2 is 10. 6 times negative 6 and negative 5 is 30. And 2 and negative 20 makes negative 40. And on the left side, I get 0. And it is 0. So that tells me that plane 1 and plane 2 are perpendicular, because they're dot products of their normals came out to 0. Take a look at the second one. Again, we're looking for a multiple. That's the quick way of doing it. Is there a multiple between these two coefficients? So 2 times, negative 2 times 6 is 12. Negative 2 times 3 is negative 6. Negative 2 times 9, oh, it's not 3. So those are not parallel. And we were on the right track at the beginning, but didn't turn out they're all parallel. So let's check our dot product again. 12 times negative 6 is negative 72. Negative 6 times 3 is negative 18. And 3 and negative 9 makes negative 27. And, well, obviously that does not equal 0. So these are neither parallel. They have no common multiple, nor are they perpendicular, because their dot product didn't come out to 0. Okay. Last idea, if we don't have parallel planes, and we don't have perpendicular planes, and they're meeting on some sort of other angle. We have this plane here, it's being intersected somehow by another plane that goes maybe through it. Right? That plane that goes through it, and it's hard to tell three-dimensionally, but that thing could be slicing through the middle at some sort of angle. Think of pages of a book. Okay, they're not meeting on a perpendicular, they're not parallel to each other, but they're meeting in a different way. Okay? If I want to figure out the angle they meet at, we go back to dot product. Same way we did when we talked about lines. Okay? But again, we're going to use normals, because the way their normals meet is the same way that the two planes themselves have to meet. Okay, so I've got two planes here in this example. They're obviously not parallel. There's no common multiple. I could test their dot product because it's part of my formula anyways, and if it came out to 0, it would tell me they're perpendicular. But if they're not, then they're going to meet at some sort of angle. So dot product, 8 plus 45 plus 1 over the coefficients of 4 squared plus negative 5 squared plus 1 squared, and 2 squared plus negative 9 squared plus 1 squared. We'll put that all in our calculators, just same old stuff we've always done, how to find angles using our dot product. And we'll get theta cos theta equals, on top, 54, and on the bottom we'll get the magnitudes of root 42 and root 86. And we'll take that all in our calculator and take the inverse of it, and theta comes out to 26. And just like lines, if we came out to an obtuse angle, we take the related acute angle. That's how we deal with angles between things. And that's planes.